Hello, everyone, and welcome to Dr. Penny Axelrad's Compass Lab. The Compass Lab stands for Clocks, Orbits, Multipath, Positioning, Attitude, and Space Situational Awareness. The point of this video is to introduce a couple of the PhD students in Dr. Axelrad's lab, as well as to tell you about some of the research that we're doing.
Hello, my name is Garrett Ryback, and I am a sixth-year PhD student in Dr. Axelrad's lab. My research is focused on inertial sensor navigation using onboard accelerometers. The challenge that I am trying to address is that deep space trajectories are perturbed by unmodeled or imperfectly modeled accelerations that causes a spacecraft to deviate away from its desired trajectory. This requires frequent ground tracking support and trajectory correction maneuvers to get the spacecraft back on track. The solution that I'm proposing is to use onboard accelerometer measurements that could enable the measurement and correction of these accelerations on board, therefore reducing the amount of ground tracking required. The approach that I am taking is to simulate the navigation of the OSIRIS-REx mission to the asteroid Bennu, where it went and collected a sample from the asteroid's surface. I will be simulating this mission in JPL's Mission Analysis Operations and Navigation Toolkit environment, or MONTI.
Hi, my name is Alex Conrad, and my research involves the Cygnus spacecraft, where we are looking at reflected GPS signals to try and estimate the sea surface height. And one of the advantages of using reflected signals like this is that you can put them on a relatively small payload, and you can also track a whole bunch of reflections, and so you get a lot better spatial and temporal resolution than you would normally with a traditional altimeter. Some of the factors that go into doing this is the precise orbit determination of the spacecraft, as well as estimating ionosphere and troposphere, and then predicting the delay from the measurement itself. And all this goes into estimating the sea surface height as a function of latitude and longitude.
Hello, my name is Chris Flood. I'm a second-year PhD student in Penny's lab. And my research is focused on laser ranging and time transfer for spaceborne PNT. So the importance of time transfer and clock synchronization on satellite clocks is that it can reduce the dependence of the satellite on the ground and improves the synchronization between satellites in a constellation that might be formation flying, that might be gathering data in remote sensing missions or things like that. So the bottom left picture here shows the basic principle of laser time transfer from a ground station to a satellite. And the sort of step further that I'm going with this is, instead of looking at ground to space time transfer, we're looking at time transfer between satellites in orbit. So this top right image here shows the constellations that I have been studying, which consist of 30 different LEO satellites in various orbital planes, along with any number of geosatellites that can help perform time transfer between all of those LEO satellites. So when all of those satellites are communicating with each other, we can get fairly small or fairly tight clock estimates, which are shown in the bottom right here. So we can get picosecond level clock estimates across this entire constellation with this particular measurement method.
I'm Davies. I'm a first-year PhD student, and my research focuses on improving orbit determination and satellite identification in the case of clustered deployments, which are deployments of usually dozens of satellites at a time. So one of the ways that we're doing this is we're using real-world data from the 2017 deployment of 88 Planet Labs satellites that you can see in the upper right. And we're simulating measurements from 4 different radar stations in North America. And we're just tuning our measurement filters and deployment methods to basically just identify the filters and deployment strategies that work best in these cases.
Hi, my name is Shayla Mutchler, and I'm a sixth-year PhD student. Up next is an excerpt from the talk I gave as part of the 3-minute thesis competition.
What if we could use space junk to observe space weather? What do I mean by this? Well, you know how you're driving along and Google Maps alerts you that there's traffic ahead? It knows that there is traffic from the information it is gathering from each car individually. When several cars start to slow down on the same stretch of highway, Google Maps uses its algorithm to identify this as traffic. My vision is to do something similar in space with space junk. As space weather ramps up, space junk slows down, and we can observe their change in speed using telescopes. I'm developing an algorithm that uses space junk data collected by our telescopes in a whole new way. It identifies trends in the overall behavior of space junk to characterize space weather. My algorithm then applies this information to improve our space weather models. This new knowledge will prevent unnecessary collisions, expand our understanding of space weather, and help us navigate space, the future frontier. Q.
Welcome to Boulder. I just wanted to show you the Aerospace Building, this is where you'll be working. It's brand new, just built in 2019, so it's really, really nice inside. And also a big reason that a lot of people come to Boulder are the mountains, which are right here. So you'll be spending a lot of time in here, but hopefully you'll also be spending a lot of time out there, if that's your thing. We'll give you a quick tour and show you around the lab. Lab. So this is where Dr. Axelrad students would normally sit and study or perform research in normal times, of course, sort of on a day-to-day basis. So we're all in this collective space where you can reach out to your neighbor and ask questions and kind of brainstorm through any problems that you might have. There are a lot of instruments over here that are used for sort of analyzing signals or power supplies, function generators, oscilloscopes, of course. Got a couple of stable oscillators, software-defined radios. There's a GPS receiver development board over there. So this black cable coming down is from a GPS antenna on the roof. So if we want to do any testing with GPS receivers or any type of anything like that, we can plug that into whatever board we want to and kind of play with it here. So this is kind of our ESD test bench, where if you're working with sort of exposed hardware like that, you want to make sure you're protected and grounded. But yeah, this is the lab. This is kind of where we do our research and where we study together.